Yeah, hi. So I'm very excited to be here. This is my first time giving a talk at a conference like this. And I'll be talking about work that my colleagues and I have been working on initially to implement this small dependently typed language Pi in miniKanren and some of the lessons that we learned along the way. There's one lesson I intended to present and another that I learned of earlier this week, which we'll also talk about very quickly. So we just got a great introduction to miniKanren from Jason. But for those who don't know, miniKanren is this minimal relational programming language. And because in relational programming, we forget about these distinctions of input and output, and this idea that for any element in an input set, there's a unique output element, a lot of really beautiful things fall out where inverse operations can be executed by the same program. And so the operation of cons and car and coulter are kind of all performed by the same program, or multiplication and division. And then in particular, evaluation of programs and program synthesis can be performed by the same tool. So when we write miniKanren interpreters, we get a lot of extra power just from one program. And today, the language that we implement in miniKanren is called Pi, which is to accompany a lovely new book called The Little Typer, and is meant as a tool to make dependent types accessible to those who don't know. And Pi is implemented in a way where it's meant to be easily understandable and kind of readily hackable, and there's a whole mathematical specification for it. And so what that means is, hey, if you're interested in miniKanren, here's a good tool which has a lot of fun properties that we can try to implement in miniKanren. And that was, at the start of this project, our goal. And our approach is to take all of the inference rules of Pi, turn them into relational programs, form disjuncts for each type of judgment that Pi can make, like type inhabitation, equivalence of expressions. And then once we have all the inference rules implemented, and we have an evaluation strategy, and we use normalization by evaluation, we will have a system that behaves like the Pi interpreter. And the relationship between inference rules and relational programs is a 20-plus minute talk on its own, so I can't get into it too much. But when we try to use inference rules by hand, right, we usually have some number of concrete terms, like the expression we want to see has a certain type, or just our general goal. And the key part of using the inference rules to make a proof is finding the other terms that we don't necessarily know, such that we can finish it. And so everything in red now we can think of as either a concrete term that we have to deal with, or some variable that we just need to solve for. And suddenly, if we have unification, a relational programming language is a great way to approach this task. There's, again, much more to say about this process, but let's assume it's kind of straightforward, and that once we have the typing rules of Pi, meaning a bidirectional type checker, we have the definitional equality of Pi, which lets us judge whether or not two expressions are equivalent or not, and an evaluation strategy, and we use normalization by evaluation, that we have a system that can do what we want. And let's see, oh, right. And so when we initially implemented Pi, we used all of the rules. And to kind of play with it more, we just thought about a subset. So the subset that we're going to think about right now has the natural numbers with their two constructors and an inductive eliminator. We have sigma and pi, which give us dependent pairs and dependent functions with the familiar cons, car, and coulter to get a witness for the property in the coulter, and then our dependent function type pi with its familiar constructor lambda and function application for elimination. We have an equality type or identity type with the constructor same, which lets us create a value that says this expression is the same thing as itself, and an inductive eliminator inequality. And this eliminator is general enough that it gives us the power of the familiar eliminators like Kong and symmetry and transitivity all in one. And then we have U, which is short for universe, and is the universe type in Pi. And so it has constructors nat, sigma, pi, and equality. So once we have this all implemented in miniKanren, we kind of want to see what we can do. And so here's the kind of synthesis we might want to run. We say, so in Pi, we create top-level definitions with two expressions, one called claim and one called define. And the first expression claims, fittingly named, the type that the definition will inhabit. And so we're claiming that we can inhabit the type that a function takes two arguments, two nats, and returns a nat. And we're claiming that with this claim for fcom, that we can inhabit the type that for any n and m which are nats, that it can be constructed that f of nm is the same nat as f of mn. If these two types are inhabitable, which they are, then that means that there is some commutative function f over nats. And that's great. And this is the type of proof-based or type-based synthesis that is kind of asking to be done with a miniKanren implementation of Pi. And what we do here is we don't give definitions for these two expressions and say, hey, miniKanren, find me something that works. Find me a function f and prove to me that it's actually commutative. And so let's try to make some pi. And what we're doing now is we're going to run with a naive implementation which uses conde to interleave attempts of all the possible inference rules, seeing which ones are applicable, and finding expressions if possible. Okay, good, it's running. And right, we can probably all think of an expression that will write a function that is commutative. So I'll think about it. But it seems to be taking our synthesis tool a while. Right, if we want to do complicated queries, this one that I just tried, it better be quicker. If only there was some way that we could stop waiting and just move on. This is a short talk. Huh. I didn't prepare for this. Oh, great. OK. So why is it so slow? And so the rest of the slides will talk about what I thought was the reason originally and what we all thought was the reason that it was so slow, which is a feature of the Pi language and our solution to that problem. But an aside is we didn't think about our miniKanren implementation and the features of the miniKanren implementation that might have been causing the slowness. And so first we'll talk about Pi, and then if there's time, we'll talk about miniKanren. So in Pi, there are 5 key type-checking relations. We have synth, which is what we use when we want to elaborate or maximally reduce an expression, and we have no expectation of its type. And so we say, right, synthesize me a type. Then we have check and is type, which also perform this maximal reduction, but which we use when we have an expectation, either that some expression is a type in the case of is type, or that it just has some type in the case of check. And then we have equivalence and equivalence of types, which in a similar relation to check and is type we use to determine that two expressions are equivalent types or equivalent of some other type. And the reason that we have two relations for check and is type and equivalence of types is because in Pi, just to keep things free of paradoxes and also easy to understand, it's simply stated that U, the universal type, is not a U. So we have this hierarchy of separate relations. And kind of the paradigm that these all follow, or many of them follow, for example, check and synth, is that there's some small number of cases that are handled directly by, for example, check or a given relation. And if check is given a form it's not expected to directly handle, it simply says to synth, you deal with it, you'll synthesize for me a type, and then if these two types are equivalent, then I'll succeed. And we have is type, which relies on check in the same way, and equivalence of types, which relies on equivalence in the same way. And kind of the problem is, if one of these initial lines is going to succeed, it's A, guaranteed to fail in the other relation, but that relation will still be called, yielding bring about a ton of extra recursion into the picture, which is just going to slow things up. And what we thought is, if we can get rid of that big, expensive relation, that this big called a synth in the case of check, then we'll be good to go. And so we have a conditional operator called condp, short for condprune, which lets us look at all the doors we have, right, and choose only maybe one or maybe just a couple to go into. And this way we'll be able to get a shorter number of lines executed. And just to show how it works before we talk about it, the same query where we want some function that's both, takes two nats and returns a nat and is commutative. And let's see how long it takes our condp implementation. Great. That's how long it should take. And we get back the constant function 0, which maybe is snarky, but it is commutative. So how does condp work? So let's talk about this relation check and see what we can say about check and how we would convert check from a conde relation to a condp relation. And that'll generally show how to use condp for anything. So check has 4 cases for this little subset of Pi. It has a case where it directly handles cons pairs, lambda expressions, and same expressions. And then it has this other rule called switch, where without any guard on the shape of xper here as it is in the inference rule, we say, well, I can say that xper inhabits the type x2 if I can synthesize that xper is an x1 and that x1 and x2 are equivalent types. This is a great rule. It helps shorten the code for check a lot, makes someone who's trying to implement all the inference rules' lives a lot easier. But since there's no guard on xper, it's going to cause us to call this, two extra recursive relations are called at every call. We really don't want to do this all the time if we don't have to. And so the way check will look as a def rel is we have these 4 cases. 3 of them start with a pattern match, which will cut off the extra work if the guard is not matched. But then switch is just kind of hanging out, ready to be called by anybody. And so what we want to do is try to compare this relation check to this weird function called x per success. So x per success, what does it do? So if the given expression looks like a pi cons expression, or a pi lambda expression, or a same expression, it returns this list of one symbol, which corresponds to its car. If x per is a var, which means a completely fresh miniKanren variable, it returns this list cons lambda same switch, and otherwise just the symbol switch in a list. And what this corresponds to is the branches, or the lines of check that could possibly succeed if x per has some given shape after reification. And that's great. OK, we can describe it in this way. We could also see it as a prescription of the behavior of check and say that x per success could tell check, if this is what x per looks like, you only need to bother expanding these lines. The others are guaranteed to fail. Don't even worry about them. And we start to see that once x per is ground, we never call both cons and switch, for example. If we assume cons refers to the cons case, lambda refers to the lambda case, same to the same case, and switch to the switch case. And this is exactly what condp does. It uses functions like this that, as of now, the user has to define, which begs for automation. But it lets us get a very hands-on control over the search and ability to drop all the lines that we don't care about. And so the way check would look as a conp relation is each line gets a name, so they can be referred to by such a function. And then we have this prelude section up at the top where check x per is given x per with a behind-the-scenes reification. And we kind of see we also can look at the expected type tau and the result of elaboration O. And there's this separation of each use of a suggestion function in a separate list. And what that does is it lets us have both minimal pruning and full generality in the case of fetch variables. We see, so x per success, when x per is a var, just says all of them can succeed as far as I know, right? And that's true. Any of these lines could succeed when x per is a fresh variable as far as we know. But if we look at the type, then maybe we can actually reduce more. Because if the type is a nat, we know only switch can succeed, because cons is never going to have it nat, and things like that. And so what we get is this kind of hierarchy of relevance where we have the most relevant variable that we look at, and if it suggests to keep looking at other variables, we do so until we have enough information to make a good pruning. And so as of now, these functions need to be written by the user. And the reason for that is because we can kind of do actually extra fancy things with conp, given that the user has complete control over the search. For the switch rule example, and this is a trick that plenty of other people have also found, is that by reordering goals, we can get better execution time. And kind of the idea is, depending on whether or not the type or the input expression to check is ground, it's better to do the synthesis first or the equivalence of types first. For switch 2, which we're going to want to use when the input expression is completely fresh, if we do an equivalence of types first, because the type is usually ground, then assuming synth is written with condp, that gives a lot of extra information into the call of synth, given that we already know some stuff about x1. And so check actually looks like this with 2 switch cases, and they're never both used at the same time, which is nice. We get to have our cake and eat it too. And so just to kind of sum up what we get to do with conp, we have this case where we want to get rid of this big giant. We can get rid of it, and we can also get rid of all the other simple cases that we didn't need. So conp lets us eliminate the unwanted disjuncts. It lets us encode more involved search strategies, and it shows us that static analysis could be a very good thing to start doing or continue doing with miniKanren queries. Thanks.
Questions for Benjamin?
So is this the if-then-else logical conditional construct from Studio?
Are you thinking of conde, condu, those operators?
Sure.
So a problem with some of the other kind of cut-like operators in miniKanren is that they don't let you run backwards, because usually the idea, and I'll just show up a conditional just to kind of say something. So if all of our variables are fresh, then the first line will always succeed. And that means that everyone else will always get dropped. And so condp kind of lets us drop lines, but in a more involved way where we don't just, the order that the goals are written won't dictate who's pruned. It's more friendly to running backwards.
So how are you going to automate it?
Yeah, so I'm glad someone asked. So looking at all the equal calls to a given variable should show the patterns that in that case they have to satisfy. And so that should be a simple enough task just to, look at all the equals that a variable has to satisfy and then create from that the suggestion function. The little decision to make is how to say, I want these to be alternates, because they can both succeed in all the same cases. It's just one is faster than the other. But a static analysis of the equal should do the trick.
I may have missed if you said this, but can conp be desugared into conde, or is it a new primitive form?
No, so it is exactly desugared into a slightly smaller conde, and that's exactly what it becomes, if that makes sense. So once this prelude has been executed and we have a list of the branches that we need to use.
No, I'm talking about desugaring the whole thing.
Oh, desugar.
So I'm thinking you could stage it as, I pick, which branch to take, and then I just do a normal conde. Does that work, or does that not work?
So, right, picking which branch to take based on something like this or something.
The predicates you have there.
Yeah, and so we look at these, choose the branch or branches we want, and then that becomes a conde with slightly fewer lines. Unless I'm missing what your point is.
I'm saying I'm asking if you can desugar that statically, rather than just doing some work and then generating based on that dynamic work a conde like.
Right. So at each different call, right, it'll need to be a different conde.
Okay.
And so that's why we have it dynamically, so that, right, I have a cons with a same inside. So first it's tailored to be a cons, and then it's tailored to be for the same expression. So for this method, dynamic makes the most sense for us.
Any other questions? I guess maybe following up from Ryan's point, can you do something like Mercury? Right, Mercury, you add special annotations, types, and whether or not you can return an infinite stream of answers and input-output modes and all this stuff, right? And then statically compiles to efficient code, right? So, how much of this could you do statically? I mean, you could do some abstract computation, but, do you think we get to the point where we're really doing all this at compile time, or much of it at compile time? Or could we JIT it, or something like that, so we're not having to execute it at runtime all the time?
Yeah. So a good question. I don't have a great answer to it. I'm sure that looking more into automating it will help expose just what can be done statically. From our tests, the suggestion functions are so cheap, it's not so bad at runtime. But I don't have a great answer, but I'm sure there's much that could be moved to compile time.